Recording is rolling. It's Monday, May 9th. So I'm gonna do some review with you guys, do some review. All right, so let's start with Unit 1 kinematics. Suppose I say you go to the edge of a cliff and you drop a ball and you want to figure out how far has the ball fallen. Do you guys remember what that equation is? Can you write it down from scratch, from memory? Hopefully you've memorized this. If not, it's technically okay because you'll have this page that you can reference, right? Won't you have this page? You know what? I did clean this all up because there was a standardized test going on here. If you really want this page in your hands, over on that lab table, I think I have a stack of them. Okay, so got these, right? Whole packet, those two things. Right, but hopefully you have this memorized. Did you guys write down what that formula is? How far is it fallen as a function of time?
1/2 GT squared.
1/2 GT squared. Right? In fact, I'll write out the expanded version of that. X equals V naught T plus half AT squared. Right? Now, if you drop it, then it is exactly what you just said, just 1/2 GT squared, because you could replace this A with the G for free fall. Okay. Hey, isn't this the college equation? If it fell for 5 seconds on Earth, you say it fell about 125 meters, right? Remember that? And if you throw it first, then you have to include this term. What about this? Now you know how far it fell. Can you tell me how fast it's going? And what equation would that be? V final equals what? V naught plus AT, right? How fast it is going is how fast it used to be going, plus acceleration times time. Right? Meters per second squared times seconds brings you back to meters per second. Right? Tag on the original velocity. Right? If you just dropped it, this goes to 0, just V equals AT or V equals GT. Right? What about this? What if you forgot to bring a stopwatch, you're not very good at counting time, but you know how tall the cliff is, and you still want to know how fast it's crash landing at the bottom. Okay? What's a good equation to use? You want to know how fast, you know exactly how tall the cliff is. Give you guys a head start. Did you guys write that one right there? The third one? Right. Remember, this one does not mention time, although time is ticking in the background. But if you ever have 3 of these 4 variables, probably good. Right? Or, hey, how many guys were thinking, I could totally set up a conservation of energy equation for that? How many guys were thinking that? Right? So here's the scenario again. Top of a cliff, you drop a ball, you know the height of the cliff, and you want to figure out how fast that ball moving right as it's about to crash land on the ground. Right? So let's get from Unit 1 to Unit 4. Unit 1 was kinematic motion, right? Unit 4 was conservation of energy. What's a good conservation of energy setup that could also answer the same question that this third equation can answer? Good call. Yeah. So sum of energy initial equals sum of energy final. Right. Oh, I should say, what is in the closed system? If I'm saying energy conservation, I'm implying a closed system, right? Okay. What is in the closed system? I'm thinking of 2 objects: the what and the what. The ball and the earth. Exactly. Yeah, this is for the ball earth system, right? The ball earth system. Exactly what you said. Potential energy at the top, kinetic energy at the bottom. Does anything cancel out? Yep, the mass. It doesn't always, especially if a spring is involved, but it's pretty common too. So it does in this case. If you solve for this V, get V is the square root 2GH, which should look really familiar because you guys have seen this over and over throughout this class, right? Okay. In fact, if you've dropped it, starts from rest, go back to this kinematic equation, this piece would go to 0. Square root both sides, square root 2AX. That looks a lot like square root 2GH, doesn't it? It's like the same thing, right? All right. How about, right. I know we did a Unit 1 here, we just did a Unit 4. You know what? While we're looking at Unit 4, let's do another Unit 4 question. Let's do a classic question I like a lot. At least classic question for my class. Does this look familiar?
Yes.
Yeah, it should. Yeah, right? Say compress it by some amount of X. Let's put point B over here. Sometimes I pick point B up here. Let's put point B right here. Let's say there's no friction, frictionless. And by the time it gets to this point, it's got some speed V and it has been lifted some height H. Okay? Set up a conservation of energy that could solve for how fast it's going if you knew like everything else. Set up a conservation of energy. Give you guys a head start. Hopefully you guys got it by about now. You guys a little more time because you guys tell me what would be in the closed system that I could even set this up in the first place. The what, and the what. Yeah, you gotta have the block, spring, and the entire Earth. Okay. Now, why would have the entire Earth? Well, a couple perspectives. One is that if you did not include the Earth, then the weight of the object would be an external force, which means it could no longer be a closed system. It would be an open system. So I couldn't even say this. Okay. Also, the fact that there's a height change. Well, what am I measuring the height with respect to? Okay, so for however we think about it, yeah, I have to have all these three objects in my closed system. So what do you guys put for this term? 1/2 kx squared. There you go. Just the energy stored in the spring. What do you guys put for the final terms? Boom. Exactly. This and this. Some of the energy goes into lifting the block against gravity. The rest of the energy goes into its speed. It's the kinetic energy. How about this? What if I doubled the spring compression, let's say from 3 centimeters to 6 centimeters, you double the spring compression. And at the same time, I'm going to quadruple the mass of the block. Right, so I just made two changes simultaneously. I doubled the spring compression and I quadrupled the mass of the block. So is the block going faster, slower, or the same speed as a result? All right, walk you guys through this. Guys, if you double the spring compression, what does that do to the overall energy in the system?
4 times.
4 times, right? Because a factor of 2 squared is like 4. So I have 4 times the energy, right? If you double it, if you compress the spring twice much, yeah, it's 4 times the energy stored in there. Right? Then if I quadruple the mass of the block, ooh, well, I could think of this, pull out factor 4 here, pull out factor 4 here. Is it gonna be the same speed either way? Yeah. Okay, so double the spring compression, quadruple the mass block, it's the same speed. Ooh, let's do a linearization. In fact, you know what I want to do actually is go back to unit 1 to do a linearization, right? So unit 1 stuff. How about this? Let's go back to the edge of that cliff, right? Edge of the cliff. And let's say there are lots of cliffs. So let's go to an alien planet. So there's gravity. We just don't know the strength of gravity field. I've got a short cliff, a medium cliff, and a tall cliff. And every one of these cliffs I measure, I'll call it height 1, height 2, height 3. Right? And I drop the ball and get time 1, time 2, and time 3. Okay. So I got, or maybe I'll even make a table. Right? So I got cliffs of different heights and different corresponding fall times. So check. Let's say there's some numbers there where the check marks are, right? Right. So you're in your little astronaut spacesuit. You just did this experiment. You gathered this data. Okay, and now you want to somehow linearize the data so that the slope of the line represents the gravity field of the planet. Okay, there's more than one correct answer. I'll set up 2 possible solutions. Okay, give you guys a little time and just come up with at least one correct answer. Okay, what could you put on each axis so that this data can become linearized so that the slope of your linear graph represents the gravity field of the planet? And what AP would probably do if they threw you this exact question is they might even give you some extra spaces in your table. So like a blank column and a blank column. So you can create manipulated axes, manipulated variables.
Height squared versus c squared?
No.
Okay.
Want all your points to line up in a straight line.
Or is it position?
Do you guys write an equation down you could start with? So this slope represents the gravity field of the planet. What versus what? Showing space here. All right. How about this? For you guys thinking some version of this, x equals, I'll skip the b naught t if you're just dropping it from rest, like 1/2 gt squared.
Yeah,
That'd be true. Okay, so you guys were thinking some version of this, right?
yeah.
Simplified version of this formula. Right now, I bet some of you guys know the answer. Give you guys a hint right there. Okay. What's one possible answer? What versus what?
X over t squared.
Okay, so x versus t squared is really close, but that would not give you a slope of exactly g. It would actually give you a slope of what?
Half.
1/2 g. Yeah, which is actually usually close enough for AT. They'll be like, okay, well, that's 1/2 g is proportional to the answer. So they're usually happy at that level. But if you want it to be exactly g, what's one way to do it? You could do what? 1/2 t squared? Yeah, you could do that. That's one way. Okay. Another way is you could go 2x versus t squared. Okay. Both of these would give you a slope of exactly g. Okay. Do you want to, you guys can linearize graphs like that? Because that takes the form like y equals an x, right? How about this? Let's do a unit 2 type question. Unit 2 is dynamics. Let's do an Atwood, classic double elevator Atwood. I'm gonna park, let's say 5 kilograms up here. Let's say 1 kilogram down here. Okay. I have a few questions about this. First question, what is the acceleration of that system? Give you guys a head start. What is the acceleration? Say the downward acceleration of the heavy one or the upward acceleration of the small one. Acceleration. If you guys are ever asked to solve for acceleration, there's 2 approaches. You might be given a bunch of kinematic stuff like times and distances and speeds, which is not the case here. So the other approach to get acceleration is to say it's the ratio of what to what. Yeah.
I can't remember if there's a
Are
two
we
there,
waiting
but
for
G, but gravity times mass 2 minus mass 1
Oh, okay. So,
Force over mass.
over mass 2 plus.
all right. Yeah. Okay. So I'm hearing different correct answers. It sounds like different perspectives. Yeah. I think everybody said something is correct. Yeah. I'm gonna start with this one. Net force on total mass, or net force on mass. Okay. That's Newton's second law of motion, right? Okay. Now, Alex, I think you're getting more into like this exact problem, which is here. Let's start put forces on this. How many newtons of force is this? 50 newtons. How many newtons of force is this guy? Right. And if I try to draw them proportionally, it should be like a 5-to-1 ratio. Right. Okay. Now, that's what you're saying is the net force would be, call this M2, call this M1, like M2G minus M1G, all divided by M2 plus M1. Right. That would be the answer in terms of variables, right? Yeah. And you could totally factor out that G if you wanted to, right? Difference over sum of masses, all times gravity field. Okay. And then if you put in numbers, now we're looking at the difference is 50 newtons and 10 newtons. So 50 newtons minus 10 newtons. Then acting on 5 plus 1 kilograms. Okay. So that's 40 newtons acting on 6 kilograms. What is 40 newtons on 6 kilograms? That's 6.67 meters per second squared. Well, if I had 3 digits of precision, then I could say that probably maybe 6.7 would be more realistic. Okay, so you guys got that?
Would anything special happen if one of those was negative, like negative mass?
Ooh, negative mass. Ooh, that'd be interesting. If it was negative mass, I guess that would imply some maybe like repulsive gravity, maybe? Is that what that would be? Right? Which would actually cause it to accelerate greater than free fall. Yeah, now that's an interesting thought. Now AP should always give you like positive masses,
Yeah,
right?
yeah.
Yeah, okay, yeah, that is an interesting thought though, yeah. So we're gonna go with gravity is always attractive, okay? And what are the boundary conditions on what this acceleration could even be? It's gotta be between what and what?
0 and 10.
Yeah, 0 and free fall, so 0 and 10 meters per second squared. Yeah, there you go, right? This looks pretty realistic to this point. Right? Here, next question. Hey, why did I not include the tensions? And because there is a tension, isn't there? Do you guys think the tension is between these two weight values? Like the tension is probably more than 10 newtons, call it F sub T, and less than the 50 newtons? And is it the same tension on both blocks? Yeah, it's the same tension. There's only one string, one tension, right? So same tension. Right? The tension is more than 10 newtons and less than 50 newtons, which would make it accelerate this way. Right? And I did not include it in this formula that we already did because it's internal to the system. See, these two forces are external to, well, they're acting on the blocks, right? Okay. So here's the next question is, what is that tension? Can you guys solve for the tension? Give you guys a head start. What is the tension in that string? All right, start walking you guys through it. Hopefully you guys beat me to the answer. Way I would do it is I would hone in on one of these blocks. It doesn't matter, either one, right? Say pick the big one. And I know that the net force acting on its own mass individually has to result in this particular acceleration. So I'll set up another F equals ma. That's this net force. Now this net force is the difference between 50 newtons downward and the tension force acting upward that I'm solving for. That will result in a 5 kilogram block accelerating downward at 6.67 meters per second squared. Okay. I'll save a little time and space here. I'm going to cut through some steps. So that times 5, subtract 50, negative of that. Okay. And are you guys getting for the tension force like 16.7 newtons? Is that what you guys getting? So about 17. So if this was an AP multiple choice answer, it might say like 17 newtons, because 2 digits. Kind of. All right, you guys pick. How about this? We done some unit 1, some unit 2, some unit 4. Oh, let's throw in it. Let's connect this to unit 4, conservation of energy. Okay. What if this whole thing moves 10 centimeters? 10 centimeters. How many meters is that? 0.1. Okay, so let's say it starts from rest and the big block falls down, the small block is going up. So a height change of 0.1 meters. Could you guys tell me how fast it's going after that time? Right. Just save a little time. Would you guys either use this third kinematic equation, or how about this exact conservation of energy, right? You guys could probably do that. Okay. Yeah, that would be for a single block. You could also, it wouldn't be G either, it would be A, like this A. Okay. Oh, what would a full conservation of energy look like for this? Do you guys think it would be a block Earth system? It'd be a block Earth system, wouldn't it? Okay. Let's do conservation of energy. Sum of energy initial equals sum of energy final.
Do we need the string?
The string we're going to consider to be massless. Right? Yeah. Right. So that's a good detail, because AP always mentions that detail. They either say light string or massless string. Okay. They might even mention frictionless, but that's it. Right. So and furthermore, you might be told that this pulley itself has no rotational inertia. Okay. So I'm going to say here, just to save some time here, that hopefully you guys are beating me to the answer anyway, that the large block falling is sort of like supplying the energy. It's all the large block has some potential energy. Okay? And as it falls, it does 3 things. It lifts the small block. Right. I will see you guys tomorrow. And also gets each block of speed. Yep.
Can we do some simple online equations tomorrow?
All right. Yeah, we'll do more review tomorrow. So I'll see you guys then. And yeah, you guys have a great rest of your day.